Google's new quantum chip, Willow, has been widely discussed for its success in error correction. Some popular science channels have even described it as performing quantum calculations in other universes. While this interpretation might be captivating for gaining public attention, we should focus on the scientific aspects. The many worlds or parallel universe hypothesis, according to a study conducted at the University of Bristol, is on the verge of being disproven. Some even claim it has already been debunked. The idea linking Willow to different universes is based on the notion that the computer's qubits, in a state of superposition, complete their calculations in other realities, with the final result reaching our universe. However, a study published in 2024 by Sandu Popescu and Daniel Collins from the University of Bristol calls for a more cautious approach to such claims. Had this study received broader attention, perhaps sensationalized reports like these would not have gained as much prominence. Physicists from the University of Bristol have published a groundbreaking paper addressing a long-debated paradox in quantum mechanics. In their study, they mathematically demonstrated that conservation laws at the quantum level hold not just statistically, but also for each individual quantum measurement. What does this mean? It could imply that the many worlds interpretation has been experimentally challenged or even disproven. The purpose of this research was to show that conservation laws, often thought to apply only on a large scale, actually hold true for every single measurement at the quantum level. Interestingly, while the scientists did not set out to target this specifically, their findings ended up questioning one of the core assumptions of the many worlds theory. This development may not sit well with some of our viewers. However, in scientific circles, this study is being interpreted as the end of parallel universe and many worlds theories. As a science fiction enthusiast, we didn't want to move forward without fully understanding whether this is truly the case. After all, the magical dreams of parallel universes from our childhood couldn't have just come to an end. Especially when Google's Willow quantum chip made headlines with claims of performing calculations in other universes. How did this conclusion emerge? Now, let's take a closer look at the scientific aspects of this significant discovery. The many worlds interpretation, developed by Hugh Everett in 1957, is a theory based on the idea that a quantum system in superposition loses at state and collapses into a single value upon measurement or due to other factors. This fascinating concept has never been experimentally proven, and with current technology, proving it seems highly unlikely. It wouldn't be an exaggeration to say that nearly half of all science fiction movies and series draw inspiration from this idea. According to the theory, when you measure the spin of a quantum system and observe a down value, the potential up value also occurs, but in another universe, since the quantum wave function does not collapse in the traditional sense. In fact, one of the most fundamental principles of physics, the conservation of angular momentum, requires that the total spin value before measurement must equal the total spin value afterward. Therefore, all possible outcomes must be realized. If the down spin occurs in our universe, the up spin must, by necessity, occur in another universe. Regardless of position or time, the total energy of a system is always conserved. While explaining this law in classical physics is straightforward, it becomes significantly more complex in the quantum realm. This new study, which challenges the many worlds theory, focuses on a major flaw identified in the conservation laws of quantum systems. In quantum mechanics, the situation shifts slightly, but the energy of a closed system is still conserved, with a key difference. In quantum systems, energy conservation is statistical. When you measure a quantum system, the energy value you obtain is random and can differ with each measurement. However, if you measure a closed quantum system 10 times, the average of these measurements will consistently yield the same result, statistically preserving energy conservation. To address a possible question up front, how can you measure a quantum system multiple times if the system collapses upon the first measurement? A valid concern. The reason this is possible is that the quantum system is recreated identically for each measurement. For example, if the average energy of the system after the first 10 measurements is 0.3, the average for every subsequent set of 10 measurements will also be around 0.3. This statistical consistency is why we say energy conservation holds in quantum systems on average, not in individual measurements. In their paper, Daniel Collins and Sandu Popescu identified the measured quantity as angular momentum. all modeling and conclusions based on this value. While it is not exactly the same, we will use spin as a reference point in our video to explain the concept more clearly. If we assume that the average value from 10 different spin measurements in a quantum system consistently results in a value of 5, we can conclude that angular momentum is statistically conserved. However, Popescu and Collins argue that conservation occurs not just statistically, but also on an individual measurement basis, much like in classical physics. If conservation holds true at the level of individual measurements, then the need for another universe to account for unmeasured possibilities would no longer be necessary. In their study, the scientists introduced an entangled preparer particle to the quantum system, which was initially responsible for creating the particle's superposition state. The closed quantum system now consisted of both the particle and the preparer. The claim is that the angular momentum conservation of this entangled system will hold true for every individual measurement, eliminating the need for statistical conservation in this scenario. They explained it as follows. In entangled quantum systems, when the spin value of one particle is measured as x, the spin value of the entangled particle will be measured as x, ensuring the total spin value or angular momentum of the system equals 0. Therefore, if the system's initial spin was 0, no matter when you perform the measurement, the total angular momentum will always be 0, just as in classical physics, where conservation holds in every single measurement. To test this idea, the researchers measured the particle, causing the system to collapse. At that moment, the spin value of the preparer particle was observed to be exactly the opposite of the measured particle's spin value. In other words, while one particle registered a spin value of +1, the other simultaneously registered -1, resulting in a total angular momentum of 0. They repeated this test multiple times, under varying conditions of time and location, and the result remained consistent. Total angular momentum was always 0. This demonstrated that angular momentum was conserved on every individual measurement, just like in classical physics, without requiring statistical methods. The fact that angular momentum is conserved in our universe, even within a single laboratory, suggests that all possible spin outcomes can occur within the same reality. This finding directly contradicts the many worlds interpretation, which proposed that unobserved outcomes must occur in separate universes. However, the study conducted by Sandu Popescu and Daniel Collins at the University of Bristol mathematically demonstrated that all possible outcomes can indeed occur within a single universe, eliminating the need for parallel worlds. Although the scientists did not make such a direct claim, their paper demonstrated that total angular momentum is conserved even in individual measurements, suggesting that multiple worlds may not be necessary. However, popular science magazines have presented this topic in a more sensational manner, framing it as the collapse of the many worlds interpretation. Of course, this perspective can be critiqued when considering non-entangled particles in a superposition state. Nevertheless, it is evident that the many worlds theory requires reconsideration. This becomes even more significant when discussing Google's Willow quantum chip, since the qubits in Willow are entangled. This study's findings suggest that Google's quantum computations are indeed occurring within our universe, not across parallel realities. In summary, while the idea of Willow performing calculations in parallel universes makes for great science fiction, it seems less connected to scientific reality based on this experimental evidence. If you subscribe to our channel, like our videos, and leave a comment, you'll be giving us tremendous support. Thank you in advance for your interest. 4-0.